Welcome to this video in which we talk about sequences and summations. So actually, um, we study sequences and summations because they denote certain patterns, um, repetitive patterns. And um, so let's start with a few examples. So for example, you have the sequence of natural integers here, or this sequence of multiple of 3, or the sequence where every number is the sum of the two previous numbers, okay, which is known as the Fibonacci sequence. So sequences arise throughout mathematics, computer science, and in many other disciplines, ranging from botany to music. So it's a very fantastic word, and in this course particularly, we are interested quite soon in using those sequences to denote the number of instructions uh, being executed at uh, regular intervals, typically in loops or in recursive functions, in iterative loops, or in uh, recursive functions, so that actually, uh, if we have a way to calculate the summation of all the terms of the sequence that describes the number of instructions being executed during a certain loop or during a certain recursive function, then we can actually have an idea about the total number of instructions being executed by our program. Okay, so it's not only sequences, but also summations of the terms in a certain sequence that are important for us, because this summation will give us an idea about the total number of instructions being executed in a certain program, whether it has several different loops or recursive functions calling one the other. So in this chapter, we will introduce the terminology to represent sequences and the sums of the terms in sequences. Um, we will give you a table that summarize this famous sums of terms of famous sequences. I will give you the proof for one of them, but in something from the next chapter, which is induction or proof by induction, we will be able to prove uh, um, sums of terms of sequences using induction and strong induction in the chapter that follows it. So those proof methods are valid, logically valid proof methods that you can add to your tool set, to the previous set of proof methods that we have talked about: direct proofs, proof by contradiction, by contraposition, and so on and so forth. So you can add induction and strong induction to this tool set, and they are particularly useful when you have sequences with regular patterns and you have a certain guess of the summation of your sequence. You may wonder how it comes that you have a certain guess about your the summation of your sequence. Well, actually, it could be a certain mathematical observation or intuition. So, for example, in ancient Greek, they remarked that the summation of the first n odd numbers has something to do with a perfect square of numbers. So maybe they watched something like the famous eggs boxes. So if you have only one um, um, one egg, then the size or the total number is equal to 1, which is 1 square. When you add three additional eggs, then you keep this squarish shape. So you have a square with four different elements. So if you add 3 to 1, then you still get 4, which is 2 square. If you add 5 other eggs to a box, then you still have a square shape. And the total now becomes equal to 9, which is 3 square, and so on and so forth. But how to prove that the summation of all the, let's call them the odd numbers, number I, from 1 to n is equal to certain um, to something that relates to n squared, okay, n or n minus 1 or n plus 1 squared. So if you have a certain guess, how can you prove it? Well, actually, you don't need to find a direct proof for this, okay? Just if you have this strong intuition about it, you can use, you just claim it, you just actually make an assumption about it and try to prove it by induction. Okay, so we close the parenthesis for induction because this is the topic of the next video. And now let's just concentrate on the terminology about sequences and sums of sequences. So a sequence is a function from a subset of the integers, usually either the set that starts from 0 or a set that starts from 1, because certain sequences, for certain sequences, the term a0 cannot be defined. Okay, it only makes sense to define it from a1 and above. So the notation a subscript n is used to denote the image of the integer n. And in this case, S would be equal to the set of AIs for I belonging to this set or to this set of integers, okay? And of course, we can rigorously define those terms. Actually, we have two different ways to define them, either iteratively or recursively, and we will see it in a few slides. So we can think of an as the equivalent of f of n, where f is a function from 0, 1, 2, 3 to s, or from 1, 2, 3, 4 to s. And we call an the nth a term of the sequence, or particularly the nth term of the sequence. So I'm going a little bit quickly on those terminologies because I think that they are not totally new for you. But you can pause the video and think about them a little bit more if you are new to sequences. So consider the sequence an, where an is equal to 1 over n. Well, this, we will see that this is a formula that defines every term in the sequence, and it's an iterative way of defining um, the terms of the sequence, because actually we are not defining every term in terms of previous terms. Okay, we are just giving a formula in terms of this iteration number n. So the total sequence would be equal to the set of elements a1, a2, a3, and so on and so forth. And if we want to enumerate them, we will just have to apply the formula on them. So 1 over 1 would give us a1, which is 1. 1 over 2 is a2. 1 over 3 is a3, and so on and so forth. Okay. Um, so again, to define sequences, we can use an iterative function such as an equal to 2n plus 3. But actually, um, it will be definable for all the terms, actually, in this case. And once you have this formula, then you can draw out the values of all the terms, a1, a2, ai, an, any term in your sequence. You have another example here. But sometimes you can better see your sequence with a recursive definition. In this case, we have to specify the base cases for the sequence. So for example, if you define every term in terms of the previous one plus 2, but then you have to provide a base case, let's say for a0 or for a1, actually, okay? Well, in this case, once you have a0, you have this formula, then you can calculate a1, because a1 is nothing but a0 plus 2, which is 3 plus 2, and finally is equal to 5. once A1 is calculated, then you can also calculate A2, and so on and so forth. Well, I think that there is a perfect equivalence between the recursive and the iterative definition. You can go from one to the other um, um, by doing some calculations, substitutions, and so on and so forth. We will do this several times, specifically when we talk about or when we prove actually properties about the about recursive algorithms later on. But just for the time being, um, um, know that you can actually go from one form to the other in a certain way. Sometimes your definition of the nth term does not only depend on the previous term, but rather on two previous terms. And in this case, maybe your base cases, you should provide more than one base case, because if you only provide A0, then you cannot define A1, because A1 depends, would have depended on A0 and A minus 1, which does not exist actually. So, or simply you didn't provide it. So in this case, actually, you have to provide two different base cases to allow you to define or to calculate the third term. And from there, you can define all the other terms as we did before. Okay, good. So I think all this material is not totally new. Add to this a quick refresher on geometric and arithmetic progression. So a geometric progression is a sequence of the form a times r squared, and so on and so forth, where the initial term a and the common ratio r are real numbers. Um, so let's consider an example. If a is equal to 2, r is equal to 5, then your sequence is 2, 10, 50, 250, and so on and so forth. Okay, so I think you can rewrite them somehow as 2 times 5, 2 times 2 times 5 square, okay, 2 times 5 cubed, and so on and so forth. So I think the element number n, you agree that it is equal to 2 times 5 to the power n, because we would have multiplied r by itself n times. And here we have an exponentially growth, actually. So we have r to the power n after the nth iteration, or um, um, at the nth turn of our sequence. And I think that maybe you already thought about this while watching the news and following up the pattern of the COVID-19 virus. I don't want to talk about it once more, but um, it's the expansion rate of this virus actually is has a certain geometric progression rate, which is believed to be around 1.24, something like that, 1.2, 1.24. And since it's greater than 1, so it means that finally it would be an exponential growth after n day. Um, and this what makes the COVID virus annoying, at least even if it has a very low mortal rate, but still it's quite annoying because it spreads exponentially. Um, and just to make the link with our work in the near future on algorithms, if you notice that a certain algorithm has a certain geometric progression in its pattern in the number of executed instruction when the input size increases, if you have a certain rate to the power n for the number of instructions, then know that you have an exponential growth. And maybe if it was about maybe sorting the students by name, and if you have only 1,000 students, then maybe you won't even notice it on your computer. But starting from a certain number, maybe after 1,100 students, you will start noticing a certain drastical um, um, decrease in the performance of your algorithm just because you reached a certain limit given your RAM, your memory capacity, and your processing capacity. Okay, another form of known sequences is arithmetic progression, where the sequence is rather um, having an additive factor, not a multiplicative one. So it's A plus D, A plus 2D, and so on and so forth. So it's kind of a polynomial growth, not an exponential growth. And this is a very reasonable growth with respect to geometric progressions. I'm not going to discuss the examples. I will leave them to you because they are quite clear. Um, Useful sequences are illustrated in this table from the textbook, and you can watch the last term among the first 10 ones. So you know that quadratic equations have a considerable order of growth already with respect to polynomial ones. Cubic have a larger impact, but before reaching n to the power n, actually, you keep increasing, but meanwhile you pass by 2 to the power n, which already gives you a very large number, even if you have a very small n. And for 2 to the power 60, computations become very tough for computers, actually. So if you have a certain encryption algorithm that has large key, let's say 64 bits keys, maybe it's very hard to crack them or to make a brute force and to try all the 2 to the power 64 combinations. Okay, so anything above 2 to the power 56 with typical computers, they are tough to compute. But even if you add more bits and you add more, if you increase n sufficiently, you make it 128, 256, and so on and so forth, then maybe even with supercomputers, you cannot compute all the possibilities within a reasonable time. Well, when you increase this factor to a bit more, of course, you get larger complexities. If you reach something like 1 times 2 times 3 times up to n, which is factorial of n, then you reach very large numbers. And this is one of the worst complexities for algorithms that you may have. But there is actually one that is even worse than that one, which is n to the power n, because it's n times n times. Okay, but already we are talking about very large complexities. One particular pattern is the Fibonacci pattern or Fibonacci sequence because it appears in many applications in computer science and engineering. While the terms do not increase that much, but still you have to know about it and to know how to program it, how to calculate it, and how to use it in the near future. Good. Plenty of details will be told about those sequences and their order of growth, but I just wanted to make a point here to show you that when an algorithm is making for an input of size n to the power 4 instructions instead of n to the power 3, then that algorithm will soon reach its limit, actually. And it's still acceptable instead of making factorial of n or n to the power n instructions, because it becomes almost intractable by nowadays computers. Okay. So the worst case can also happen by accumulating all those numbers. So what if you're executing your code for one time, for 4 times, 9 times, 16 times, 25 times, up to 100? Okay, so is it the same as just doing 100 instructions? I think, and you will see that it's even worse, actually, because accumulating all these numbers, like the sum of all these numbers, is something to the order of n cube. Okay, and doing all of these the total of all of these terms is something to the power of four, and so on and so forth. The proof, like just an intuition, um, if you're doing n iterations when you have an input of size n, I mean, if it takes you n instructions to let's say search in a list of n students for a student with a specific name, then you have a polynomial algorithm. So the complexity is very reasonable. Uh, but actually, if you should do one instruction, then do two instructions, then a three, and then n minus one, and then at the end, n instructions. Well, in this case, your algorithm is not polynomial anymore. All these instructions will add up, will actually accumulate until having something to the order of n squared. And we have talked about this in the introduction session, I think, and at several different occasions. Um, it's something like n times n um, plus 1 over 2. Okay, so we can prove it in several different ways. One of them is by induction. So you can do it quite soon by induction and show that it becomes something quadratic, not polynomial. So this is why it's important to know that summations, the summation of the terms of a certain sequence may change the final outcome. It's not equivalent to an itself, but it's something maybe bigger than the last term in the sequence. Okay. Um, well, first of all, what's the notation for the summation? So if you have terms am plus 1 up to an, and you want to talk about their sum, well, just denote it in this way. So use the sigma symbol and say it's the summation of all the aj from j equal m to n. Okay. You can also write it in this way or in this third manner. So we will use this one particularly in this course and in the exams, but just be familiar with the two other notations just in case you see them in any other textbook or online. The variable j is called the index of summation. And this is quite similar to what you do in loops. If you are already familiar with iterative programming and use for loops, particularly in C++, or Java, maybe you're used to use for j equal m or a certain initial case, j less than or equal to n, because when we write the summation in this way, we mean that we start from am and we end at an included j plus plus, and then you're making in a certain accumulating in a certain variable sum, the previous sum plus. If you're not familiar with this notation, I would remove the plus from here and I would put it after the equal, sum equal to sum plus a number j if you have an array of n elements called a, and you can iterate over all these elements aj's. Okay, so this is exactly what you would do in programming languages to denote this summation, and this is why this j is called the index of the summation or the index of the iteration in coding. So it runs through all the integers starting from its lower bound or limit m and ending with its upper bound n. Okay, more generally for a set S, we can talk about the summation of all the AJs for, well, I think that we should say that AJ belongs to S. I should correct this in the slides, okay? So we are talking about the summation of AJs for every AJ belonging to our set, okay? I'm sorry for the J, it should be a subscript written below A, okay? Good. Examples. R to the power 0, R to the plus R to the power 1, up to R to the power n is the summation here. Okay, Rj, I think to be how to say, like actually to stick to the notation that we just saw, we should add j below. Okay, so it's the summation of the rj's for j r to the power j, actually, for j equals 0 up to n, okay? And 1 plus 1 over 2, and so on and so forth. Without the boundary here, it's the summation of the terms 1 over I from I equal 1 to the infinity. Okay, so maybe in certain books they would use this abbreviation, but I recommend that you clarify which index you are talking about, because sometimes we can talk about two different indices in our summation. So we can talk about, let's say, the summation of I times um, I minus j, suppose, and maybe we are taking j's from 0 to n, and we are taking I from also from 0 to n. Okay, so we can have something like this, and it's really good to have an idea about which index you are using in your summation. Good. And this is particularly useful when you want to talk about nested loops in programming. Okay, we will get back to this later on. So what about products? We can also talk about the products of terms of a certain sequence. Well, in this case, we use this capital Pi symbol, and we use the same lower limit and upper limit with the indices in subscript. So as usual, and this represents the multiplication of all the terms up to an. Okay, so nothing new. I think you are familiar with those notations. How to calculate sums? Well, actually, the perfect tool is proof by induction. On condition that you have a certain assumption or intuition about the value of that summation, okay? But, well, how to make this assumption, how to build this intuition? Well, you have to draw out all the possible summations for n equal to 0, for n equal to 1, 2, 3, and so on and so forth. Okay, as I said, for the summation of the odd numbers at the beginning of this video. Okay, so once you have this intuition, well, you can then proceed with proof by induction later on. But sometimes you can also proceed with a direct proof. So here we are giving you a direct proof for the for proving that the summation of terms of a geometric progression from 0 to n is equal to this magical formula here, if r is different than 1, and to this formula here, if r is equal to 1. There is a tiny trick to prove this with a direct proof. So the trick is to multiply the summation by r, okay? And then we'll make also another trick in few steps. So it's known that this summation actually, as number n, is equal to the sum of all the arj from j equals 0 to n, okay? So by the way, we can unfold it here just to make sure that we are understanding what's happening. So it's a times r to the power 0 plus a times r to the power 1 plus, and so on and so forth, a times r to the power n. Okay, so from j equals 0 to n included. Good. What if we multiply this summation by r? Okay, so don't forget, we want to make sure that this is equal to that thing here. Okay, so how to get rid of this summation? Let's do some tricks. Actually, we want to get on this side, we want to get Sn again, so that we can actually plus this term here, okay? Then when we take Sn to this left-hand side, okay, we get Sn factor r minus 1, and then we get the r minus 1 to this side on the right. Okay, don't worry if you don't get it right now, but just like follow the steps with me, please. So let's multiply both parties with r. Doing so would make your right-hand side equal to what? Equal to a times r to the power 1 plus a times r to the power 2. So we're raising all the powers, plus a times r to the power n plus 1. Okay, so it's a times r to the power j plus 1 from j equals 0 to n. Or you can alternatively see it in this way. So this is also equivalent, okay, to this thing here. It's the summation from k equal 1 to n plus 1, okay? So from k equal 1 to n plus 1 of a times r to the power k. We don't need to change j into k, guys, but yeah, just if you feel more comfortable about it, because in this case, we would say that k is equal to j plus 1, okay? But it's the same. We could also use j and make j in this time ranging from 1 to n plus 1, okay? Good. Well, you can do a certain surgery to this summation, okay? Let me do it on the unfolded summation. So this one can be rewritten in this way. I can make it as follows. So if I want to start once again from k equal to 0 to get back to Sn, because this summation is equal to Sn, I can add a at the beginning times r to the power 0, so which is a times 1, and then I can subtract a at the end, and I would leave this summation intact, okay? So let me start with AR0 and let me add to it all those terms here, okay? So a to the power r plus 1 will be grouped with this minus a, okay? But from a r1 to a times r to the power n, I will add them to this AR0, okay? I have the right to add this one because I subtracted from that side. So the final value is really equal. So those two summations are 100% equal. So I would add a times r to the power 1, a to the times r to the power 2, up to a times r to the power n. Okay, so I'm preserving all the terms that I had earlier. Okay, even this one. I'm adding a at the beginning and subtracting a from the end. Adding a at the beginning can be seen as adding a times r to the power 0, no matter what r is, okay, because r to the power 0 is equal to 1. Good. And now I can see my summation as Sn itself plus those terms. So it's really equal to Sn plus a times r to the power n plus 1 minus a. So do you see the trick? So now I can get as to that side and then divide by isolated and divide by r minus 1, I would get the target value that I wanted to prove. Okay, so please try once again, print this slide and try to, the previous slide, and try to do it by hand yourself to convince yourself that there are no tricks. Okay. And this is true if r is different than 0, and you have also the obvious case where r is equal to 1. It's just the summation of a times a times a n times, which is n plus 1 starting from 0, so it's n plus 1 times, and this is why it's n plus 1 times a. Okay, so please don't forget when you go from 0 to n included, okay, you are summing up a with itself n plus 1 times, because you're adding a for j equal to 0, for j equal to 1, and so on for j equal to n. The number of steps here is equal to the last term, which is n, minus the first term, which is 0, and the plus 1, okay? So if I summing up a for, let's say, j equal 14 up to 16 included, okay? There are no 2 elements only. There are, in fact, the 3 elements, because I will add it for 14, I will add it for 15, and I will add it for 16. So usually the number of items that I have here, it's equal to 16 minus 14, but plus 1. Okay, so don't forget to do this. So which is equal to 3. I have 3 items between 14 and 16. Okay, and the this general rule applies also here, and you have actually n plus 1 terms, not only n terms. Okay, good. We have some ready recipes for useful summations that recurrently appear in computer science and typically in the study of the complexity of algorithms. Um, so we have this one that we have just proved. You have some others that relate to calculus, and they have been proved in the textbook, but many of those will be proved by induction in the upcoming chapter, either in the slides or in the exercises. Okay, and I just want you to notice that when you do a certain effort for one time, two times, three times, and so on, and then n times, well, the total effort would be something equivalent to n squared. And when you do the effort for 1, 2, plus 3, plus 4, up to n squared, then your total effort is something relating to n cubed. Okay, so you have n times n times n. Okay, so it's rather n cubed, and so on and so forth. Okay, so I just want to draw your attention to this characteristic of accumulating work. So I think we reached the last slide. I hope that this deck of slide is relatively easy for you. It only includes some notations and some pointers for the use of sequences, whether iterative sequences or recursive sequences in the upcoming chapters will pass by induction, proof by induction, and strong induction before starting the most important part that relates to the study of complexity of algorithms in the near future. Thank you for watching, and see you soon.